paragraph in question does not apply strictly to an emergency system that employs transfer equipment. National Electrical Code Section 700.5b permits the alternate power source, like a generator, to supply emergency, legally required, and optional system loads. This is contingent upon automatic selective load pickup and load shedding being implemented. This ensures adequate power is delivered in a specific order of priority, firstly to emergency circuits, secondly to legally required standby circuits, and thirdly to optional standby circuits. Therefore, in a system where a generator supports the entire facility, a transfer switch is not necessarily mandated to isolate legally required emergency systems. Considering the scenario presented, where existing emergency lighting relies on battery ballasts without a dedicated emergency circuit, there is no explicit requirement to redesign the new system to incorporate separate circuits solely to provide the required level of emergency lighting and power. However, it's important to acknowledge the potential for neglecting battery ballast maintenance once the generator assumes the facility's power needs. While not mandatory, consideration should be given to installing a new emergency lighting system independent of the generator-powered system. This ensures the continuous availability of emergency lighting. It's crucial to understand the implications of Section 700.5b within the National Electrical Code. This section offers flexibility in how emergency power systems are designed, particularly when integrating a generator for comprehensive facility backup. The key is the implementation of automatic selective load pickup and load shedding. These features are paramount in guaranteeing the reliable operation of emergency systems during power outages. Selective load pickup refers to the automatic connection of essential loads to the generator in a predetermined sequence. This prevents overloading the generator and ensures that critical systems receive power first. Load shedding, conversely, is the automatic disconnection of non-essential loads to maintain the generator's capacity and stability. By shedding less critical loads, the generator can dedicate its resources to powering emergency circuits and legally required standby systems. When evaluating the necessity of a transfer switch, several factors must be considered. Firstly, the size and complexity of the facility play a significant role. Larger facilities with numerous critical loads may benefit from transfer switches to isolate and protect emergency systems. Secondly, the specific requirements of local codes and regulations should be carefully examined. Some jurisdictions may mandate transfer switches for certain types of emergency systems. Thirdly, the risk tolerance of the facility owner should be taken into account. If uninterrupted power to emergency systems is paramount, a transfer switch can provide an additional layer of protection. Regarding the maintenance of battery ballasts, it is essential to establish a proactive maintenance schedule. Regular inspections and battery replacements are crucial to ensure the reliable operation of these systems. Even with a generator backup, battery ballasts should not be neglected. They serve as a secondary source of emergency lighting in the event of generator failure or maintenance. In summary, while Section 700.5b offers flexibility in emergency power system design, it is crucial to thoroughly evaluate the specific needs of the facility. Factors such as load shedding, selective load pickup, local codes, and risk tolerance should all be considered. Furthermore, the maintenance of existing emergency lighting systems, such as battery ballasts, should not be overlooked. Let's delve a little deeper into the technical aspects of automatic selective load pickup and load shedding. These functionalities are typically implemented using sophisticated control systems and monitoring devices. The control system continuously monitors the power supply and the status of various loads within the facility. In the event of a power outage, the control system automatically starts the generator and initiates the selective load pickup sequence. The control system energizes the emergency circuits first, followed by the legally required standby circuits, and finally the optional standby circuits. The timing and sequence of load pickup can be customized to meet the specific needs of the facility. Load shedding is typically implemented using a combination of sensors and relays. The sensors monitor the generator's output and detect any signs of overload. If an overload is detected, The control system automatically disconnects non-essential loads to reduce the generator's burden. Selection of loads to be shared can be based on a variety of factors, such as their priority, their power consumption, and their impact on critical operations. It's also worth noting that emergency lighting systems can be designed using a variety of technologies, including LED fixtures, fluorescent fixtures, and incandescent fixtures. LED fixtures are becoming increasingly popular due to their energy efficiency, long lifespan, and instant-on capability. Fluorescent fixtures are also energy efficient, but they may take a few seconds to reach full brightness. Incandescent fixtures are the least energy efficient and have the shortest lifespan. When selecting emergency lighting fixtures, it's important to consider the illumination levels required by local codes and regulations. The illumination levels must be sufficient to allow occupants to safely evacuate the building in the event of a power outage. In addition to the type of lighting fixture, the placement of emergency lighting is also critical. Emergency lights should be located along exit routes, in stairwells, and in other areas where occupants may need to navigate during a power outage. The spacing between emergency lights should be such that the required illumination levels are maintained throughout the area. It is always important to consult with a qualified electrical engineer or contractor to ensure that the emergency power system is designed and installed in accordance with all applicable codes and regulations. A properly designed and installed emergency power system can provide a critical lifeline during a power outage, ensuring the safety and well-being of building occupants. The National Electrical Code, or NEC, provides comprehensive guidelines for the design and installation of electrical systems, including emergency power systems. It is essential to adhere to the NEC requirements to ensure the safety and reliability of these systems. Section 700 of the NEC specifically addresses emergency systems. This section covers topics such as the scope of emergency systems, the types of equipment that are permitted, the wiring methods that must be used, and the testing and maintenance requirements. One of the key requirements of Section 700 is that emergency systems must be designed to automatically transfer to an alternate power source in the event of a power outage. This can be accomplished using a transfer switch or other approved means. The NEC also requires that emergency systems be tested regularly to ensure that they are functioning properly. These tests must be documented and maintained for inspection by the authority having jurisdiction. In addition to the NEC, there may be other local codes and regulations that apply to emergency power systems. It is important to consult with the local authority having jurisdiction to determine the specific requirements for a particular installation. Understanding the different types of loads is also important. Emergency loads are those loads that are essential for life safety and must be powered during a power outage. These loads typically include emergency lighting, fire alarm systems, and critical medical equipment. Legally required standby loads are those loads that are required by law to be powered during a power outage. These loads may include elevators, ventilation systems, and other equipment that is necessary for the continued operation of the facility. Optional standby loads are those loads that are not essential for life safety or legally required, but that the owner may choose to power during a power outage. These loads may include computers, office equipment, and other non-critical systems. The selection of an appropriate generator size is critical to the proper functioning of an emergency power system. The generator must be sized to handle the total load of all the emergency, legally required, and optional standby loads that will be connected to it. It is important to consider the inrush current of motors and other equipment when sizing the generator. The inrush current is the surge of current that occurs when a motor is first started. The generator must be able to handle this inrush current without experiencing a significant voltage drop. The installation of a generator requires careful planning and coordination. The generator must be located in a well-ventilated area and must be protected from the elements. The generator must be connected to the building's electrical system in accordance with all applicable codes and regulations. It is also important to install a fuel storage system that is adequate to meet the generator's fuel consumption requirements. The fuel storage system must be designed and installed in accordance with all applicable codes and regulations. Regular maintenance is essential to ensure the reliability of an emergency power system. The generator should be inspected and tested regularly to ensure that it is functioning properly. The fuel storage system should also be inspected regularly to ensure that it is free of leaks and contamination. It is also important to perform regular load bank testing to verify that the generator is capable of handling its rated load. Load bank testing involves connecting the generator to a resistive load bank and measuring its output voltage, current, and frequency. This test can help to identify any potential problems with the generator before they cause a failure. When dealing with existing emergency lighting systems that utilize battery ballasts, it's crucial to understand their limitations and potential drawbacks. Battery ballasts are self-contained units that provide backup power to lighting fixtures in the event of a power outage. They typically consist of a battery, a charger, and an inverter. The battery stores energy and the inverter converts the direct current from the battery to alternating current to power the lighting fixture. One of the main limitations of battery ballasts is their limited runtime. The battery can only provide power for a certain amount of time, typically 90 minutes to 2 hours. After that, the lighting fixture will go out. Another limitation of battery ballasts is their dependence on the battery. If the battery is not properly maintained or if it fails, the battery ballast will not function properly. This can leave occupants in the dark during a power outage. Furthermore, battery ballasts can be expensive to maintain. The batteries need to be replaced periodically, and the charger and inverter may also require maintenance. It is important to factor these costs into the overall cost of ownership when considering battery ballasts. When evaluating the option of installing a new emergency lighting system separate from the generator-powered system, several factors should be considered. Firstly, the cost of the new system should be weighed against the benefits. A separate emergency lighting system can provide a higher level of reliability and redundancy, but it will also add to the overall cost of the project. Secondly, the available space for the new system should be considered. A separate emergency lighting system will require its own dedicated wiring and equipment, which may take up valuable space. Thirdly, the maintenance requirements of the new system should be considered. A separate emergency lighting system will require its own dedicated maintenance schedule, which may add to the overall maintenance burden. Ultimately, the decision of whether or not to install a new emergency lighting system should be based on a thorough evaluation of the specific needs of the facility. It is important to weigh the costs and benefits carefully and to consult with a qualified electrical engineer or contractor. In conclusion, the design and installation of emergency power systems is a complex undertaking that requires careful planning and coordination. It is essential to adhere to all applicable codes and regulations and to consult with qualified professionals to ensure the safety and reliability of these systems. By understanding the principles of emergency power system design and the requirements of the NEC, you can help to ensure that your facility is prepared for a power outage. Remember to consider the specific needs of the facility, the available space, and the maintenance requirements when making decisions about emergency power systems. A well-designed and maintained emergency power system can provide a critical lifeline during a power outage, ensuring the safety and well-being of building occupants. Let us consider some specific scenarios to further illustrate the concepts discussed. Scenario 1: a hospital operating room. In this critical environment, a generator is essential to maintain life support equipment and surgical lighting during a power outage. A transfer switch is typically required to isolate the operating room's electrical system from the utility grid and connect it to the generator. The transfer switch ensures that the operating room receives uninterrupted power from the generator, even if the utility power is fluctuating or unstable. Scenario 2: a high-rise office building. In this type of building, emergency lighting and fire alarm systems are essential for life safety. A generator is typically used to power these systems during a power outage. Automatic selective load pickup and load shedding are implemented to ensure that the emergency lighting and fire alarm systems receive priority power. Optional standby loads, such as computers and office equipment, may be shared to conserve generator capacity. Scenario 3: a data center. In this critical facility, uninterrupted power is essential to maintain the operation of servers and other IT equipment. A generator is typically used to provide backup power in the event of a power outage. A redundant power system consisting of 2 or more generators and transfer switches may be implemented to provide an even higher level of reliability. Scenario 4: a small retail store. In this type of business, emergency lighting is typically the only essential load. A battery ballast system may be sufficient to provide backup power to the emergency lighting fixtures. A generator may not be necessary unless the store is located in an area with frequent power outages. Scenario 5: a manufacturing plant. In this industrial setting, critical machinery and equipment may need to be powered during a power outage. A generator is typically used to provide backup power to these systems. Automatic selective load pickup and load shedding are implemented to ensure that the critical machinery and equipment receive priority power. Non-essential loads, such as lighting and HVAC systems, may be shed to conserve generator capacity. These scenarios illustrate the wide range of applications for emergency power systems. The specific requirements of each application will vary depending on the type of facility, the critical loads that need to be powered, and the local codes and regulations. It is important to carefully evaluate the specific needs of each application and to design an emergency power system that meets those needs. The evolution of emergency power systems continues to advance, driven by technological innovations and increasing demands for reliability. One notable trend is the growing adoption of microgrids. Microgrids are localized power grids that can operate independently from the main utility grid. They typically consist of a generator, renewable energy sources such as solar panels and wind turbines, and energy storage systems such as batteries. Microgrids can provide a more resilient and reliable power supply than traditional emergency power systems. They can also reduce reliance on fossil fuels and lower carbon emissions. Another trend is the increasing use of smart grid technologies. Smart grids are advanced power grids that use sensors, communication networks, and control systems to optimize the flow of electricity. Smart grids can improve the efficiency and reliability of emergency power systems. They can also enable more sophisticated load shedding and selective load pickup strategies. Furthermore, advancements in battery technology are enabling the development of more compact and efficient energy storage systems. These energy storage systems can be used to provide backup power for critical loads during short-duration power outages. They can also be used to smooth out the fluctuations in power from renewable energy sources. The integration of renewable energy sources into emergency power systems is also becoming more common. Solar panels and wind turbines can provide a clean and sustainable source of backup power. However, it is important to carefully consider the intermittency of renewable energy sources when designing emergency power systems. Energy storage systems are often needed to provide backup power during periods when the renewable energy sources are not generating electricity. The development of new and innovative emergency power system technologies is ongoing. Researchers and engineers are constantly working to improve the performance, reliability, and sustainability of these systems. As technology continues to evolve, emergency power systems will become even more critical for ensuring the safety and well-being of people and businesses during power outages. The regulatory landscape surrounding emergency power systems is also constantly evolving. Codes and standards are updated regularly to reflect the latest technological advancements and to address emerging safety concerns. It is important to stay informed about the latest regulatory requirements to ensure that emergency power systems are designed and installed in compliance with all applicable codes and standards. The National Fire Protection Association, or NFPA, is a leading organization in the development of codes and standards for emergency power systems. NFPA 110, Standard for Emergency and Standby Power Systems, provides comprehensive requirements for the design, installation, testing, and maintenance of emergency power systems. NFPA 17 National Electrical Code also contains requirements for emergency power systems. It is important to consult both NFPA 110 and NFPA 70 when designing and installing emergency power systems. In addition to the NFPA codes and standards, there may be other local codes and regulations that apply to emergency power systems. It is important to consult with the local authority having jurisdiction to determine the specific requirements for a particular installation. The enforcement of emergency power system codes and standards is typically the responsibility of the local authority having jurisdiction. This authority may be a building department, a fire department, or another government agency. The authority having jurisdiction will typically conduct inspections to verify that emergency power systems are installed in compliance with all applicable codes and standards. Failure to comply with emergency power system codes and standards can result in fines, penalties, and even the shutdown of the facility. It is therefore essential to ensure that emergency power systems are designed and installed in accordance with all applicable requirements. The future of emergency power systems will likely be shaped by several key trends, including the increasing demand for reliability, the growing adoption of renewable energy sources, and the development of new and innovative technologies. As power outages become more frequent and severe, the demand for reliable emergency power systems will continue to grow. Businesses and individuals will increasingly rely on these systems to maintain essential operations and to ensure the safety and well-being of people. The integration of renewable energy sources into emergency power systems will also become more common. Solar panels, wind turbines, and other renewable energy sources can provide a clean and sustainable source of backup power. However, it will be important to address the intermittency of these sources through the use of energy storage systems and smart grid technologies. New and innovative technologies will continue to emerge, further enhancing the performance, reliability, and sustainability of emergency power systems. These technologies may include advanced battery systems, fuel cells, and microgrid control systems. As these technologies mature and become more cost-effective, they will be increasingly adopted in emergency power system applications. In closing, remember to always prioritize safety when working with electrical systems. Emergency power systems can be dangerous if not properly designed, installed, and maintained. Always consult with qualified professionals and follow all applicable codes and regulations to ensure the safety of yourself and others.